wow. I don't think I thought we were supposed to make it.
That's fucking hilarious.
I don't know, I just realized you can
Keep doing you. Keep doing you. Do you.
I'm sitting on the wrong side today.
Jen is shorter than you, so I can see over.
That's true.
It's so true.
Well, I mean, I should be. I'm kind of like half insult, half compliment.
Well, you go like this, so that's good sometimes.
Yeah.
But when
It's
you
usually me falling.
Jen, I've been very jealous of you this past week for going to Blackies, yes.
Blurry? I can read it, but I get that from
It's very confusing. You did, of course.
Okay, so I did all
I don't even need it.
No, you need to.
Yeah?
I got marked off on my last one because I didn't do it for so.
All right, please make sure your name is on the lab report. Please pass it
Do you have a picture?
side. Go ahead and pass it over to the right side, please.
I will not accept that.
As always, make sure your name is on it.
Shut up. That was
Pass it down.
Has a senior ever disrespected you guys in any way?
Senior.
Any additional labs? If you.
Seriously?
Like seriously. Like no, be like. Or like even like screw with you.
All right, guys at my desk, stay there. Let me just come in and grab it. One more. All right, before we begin today, the moment you've all been waiting for.
Ready, guys? The answers to the test for this year.
No, 21st.
No, this is definitely the moment you've been waiting for.
Oh.
I love you, Mr. Shallot.
It's the fall semester extra credit project.
Wait.
I don't know if I'm gonna do this.
I'm definitely.
If it's a group project, I'll do it. If it's by myself, I'm not doing it.
Mr. Shallot, our test next week is on
It's
Monday.
on Thursday of next week.
Is it the 20th?
All right, let's take a look here at the extra credit project for the fall semester. Wait, down please. You have two options. Either of the options, it's turned in the exact same way via the website turnitin.com. So the first thing you have to do is register with the class ID and the password here. Password is the same for everybody, it's just Pally. It's a lowercase p. Now, regardless of which option you do, the window for submitting your paper is the same for both. It opens on Monday of next week at midnight, it's the 17th of November. It then closes at nearly midnight, 11:59 p.m. on Friday, December 12th. Because you have more than 2.5, it's almost 3 weeks to do this assignment, that means that I'm not going to accept any late papers under any circumstances, no excuses. Okay, your paper will be checked for plagiarism. Plagiarized papers will not receive any extra credit, and you'll be reported to Dean Howard. Okay, now here is option number one. You are to choose one of the following topics and write at least a 4-page double-spaced paper, not including any pictures or diagrams. In other words, I want to see at least 4 pages of text. You are to write about one of the topics listed below. You'll see those in just a moment. And your paper must address the described subtopics. Include a bibliography with at least 3 sources, and I want you to try to follow MLA format as closely as you can. You must also cite your sources within the body of the text. Failure to do so will result in a low score. Now, here's what I mean by that. Anytime that you present factual information, like for example, you say the radius of the sun is blah, blah, blah. You have to say where that came from. You have to cite it specifically within the text. Once again, try to use MLA format, doing so as closely as you can. Okay, now you are welcome to use websites as resources, but I will not accept citations or bibliography from illegitimate sources, such as Wikipedia or other non-peer-reviewed sites. Now, here's what I mean by that. What Wikipedia and like-minded sites are good for is giving you an overview of an individual topic, and usually at the end of the article, there will be numerous links to the actual science. Like if you look up a Wikipedia article on the sun, there'll be a link at the bottom of the page that will point you towards a NASA website, for example. That's what those types of sites are good for. They can kind of point you in the right direction, but when it comes to actual sources that you cite and use as bibliographical information, I want you to get as close to the actual science as you can. Government agencies, for example, universities, and so on. So stuff like Wikipedia is good for giving you an overview and pointing you in the right direction, but that's essentially the extent at which you can use a site such as that. Okay, now the assignment has a maximum score of 25 points, and it is just 25 points of extra credit, so it's just piled on top of your grade. But I will be checking briefly your grammar, spelling, and quality of writing. Submitted papers that are less than 4 pages in length will not receive the full credit. Now on the subsequent pages, take a look. I provide for you here 10 options, and of course you just choose one to write a brief paper about. Your paper does have to address the described subtopics that you see here. Now when it comes to these individual topics, there's a whole host of interesting stuff here. When it comes to researching your topic, finding legitimate peer-reviewed sources for the topic, believe me, is going to be the least of your problems. There's a huge amount of information out there from legitimate peer-reviewed sources for any of the topics that I have listed here. So look over the topics, choose something that interests you, start to do a little bit of research on it. Believe me, you're going to have no trouble at all in finding information. Now that's option number 1. Take a look at option number 2. The option number 2 on the last page is turned in exactly the same way as number 1 via turnitin.com. Once again, the window for submission is exactly the same. Now option number 2 has to do with a specific event. There is an open house that is conducted by the UCLA Department of Physics and Astronomy, their College of Engineering, and also their departments of Chemistry and Earth Science. That open house is being held this Sunday at the UCLA campus. It's from approximately noon until 5 p.m. Sometimes it goes a little bit into the evening as well. If the weather's clear, they bring out telescopes. They also sometimes have some planetarium shows as well. The details of the actual open house, and it's quite good, I go virtually every year, can be found here at this individual website. Now, if you attend the open house, you'll receive 25 points of extra credit, but in order to receive the points, though, you must answer 3 of the following questions, which are on the remainder of the handout, describing your experience, as well as attach a photograph of yourself beside an exhibit to prove that you attended. Now turn to the back side, specifically number 8. Here is then the brief write-up that you do about your experience, basically, as I said, answering 3 of the previous questions that I have provided here for you. Your paper in this case must be no less than 2 pages double-spaced, once again not including any diagrams and or photographs, so 2 pages of text. Your grammar, spelling, and quality of writing will once again be assessed. Submitted papers that are less than 2 pages in length will not receive full credit. Don't forget, however, to attach a photograph of yourself to the end of your paper. So the easiest thing to do is if you type it up, say, on Microsoft Word, attach a JPEG of yourself to the very end, convert the whole thing into a PDF, a single file, and then just upload that to turnitin.com. That's basically option number 2. Now with the open house, as I said, they do a really good job of it, and it's for the public, so it's all going to be at a relatively, I don't want to say dumbed down level, but at a level where everybody could approach it. And what I primarily go for actually are the talks and the lectures that are given by the actual scientists. So for example, a couple of years ago, one of the talks that was given by the team of astronomers that examined the Milky Way's supermassive black hole. The people that actually do that research, that was one of the talks. So that's primarily what I go for, is those types of presentations. But if you think about it, if you're free on Sunday and you think you can do it, that's a nice, easy way to get your extra credit. If you're not interested or you're busy, then of course you can do option number 1. Questions, Tatum?
Can we do both?
No, just one.
Okay, and also, what if you're presenting something there?
Huh?
What if you're presenting, like...
You're part of the presentation?
Yeah.
Really?
Because our robotics group...
Oh, okay.
So.
Boy, that's the first time it's ever been asked. See me after class, we could work something out. Okay, yeah.
Do we have to stay for the whole 5 hours?
No, but you probably want to give it at least 2 hours, though, to get enough information, whatever it is that you're interested in, to be able to write up a short paper. Okay, if you're there for an hour, frankly, it's probably not enough time. 2 hours is usually pretty good. I usually go for a couple of hours. Okay, Talia?
So for number 6 and 7, you don't necessarily need to answer if you never.
Right, so I gave you a bunch of choices about which you could write up a short paper on for object number 2, or option number 2. Just basically answer 3. Okay, so it's just a few paragraphs for each option. So, yeah.
Extra credit, so it's 25 out of 25.
It's just 25 points piled on top of your grade. Okay, it's just, everything is just points. Nothing is weighted differently according to my scheme. So I just add the 25 points into your grade at the very end of the semester. Okay, that's the easiest way to do it. Anything else? Yes, Jen?
This is going to be the last unit test before the
Oh, our
final.
test next week. It is our last unit test prior to the final. That's
Okay.
correct. Okay, it won't be until next week. Speaking of our last unit here, or our unit before we get to our next unit test, it is. Let's go ahead and get started. Put this aside, please. Take out your notes.
Wait a second.
I helped the segue. That's good. I can help.
Okay, now here's where we were at the end of class last time, if you recall. I started the process of Newton's unification, using the law of universal gravitation to first of all explain the motion of projectiles near the Earth's surface. That's where I ended with last time in class. And now here at the beginning of class today, here's the second part of the unification. Now we want to use the exact same physical principle, the law of universal gravitation, to explain, for example, Kepler's laws. Let's take a look at that in the following manner. Anna? Okay, now remember Kepler's first law of planetary motion, that is the planets orbit the sun in elliptical orbits, not in perfect circles. Now, Newtonian gravitation does predict elliptical orbits for planets about the sun, but to show that explicitly requires two-dimensional calculus in polar coordinates. That's beyond the scope of this class. So what we're going to do is we're going to simplify. We'll simplify such that we can do this algebraically by assuming that all the planets orbit the sun in uniform circular motion. And then with that simplification, we'll look briefly here at Kepler's second and third laws. Okay, now here's what we go about doing. We first of all have here, for simplicity, a planet in uniform circular motion about the sun. Right here is the sun, which has some mass. We'll call that m sun. Okay, and then we have the planet itself here. It has mass m. And the distance between the sun and the planet is our distance small r. Okay, that distance is also going to be the radius of the orbital circle. And now here's how we apply F equals ma. According to Newton, there's only one force exerted upon the planet, and that's from the sun's gravity. So from last time in class, remember that the law of universal gravitation is the following expression. First of all, the gravitational constant, capital G, times the mass of the sun, times the mass of the planet, divided by the distance between the 2 points here squared. And then on the right-hand side of the equation, we just have mass times acceleration. The acceleration in this case, however, is a centripetal acceleration inwards towards the center of the circle that is pointing directly at the sun. So on the right-hand side of the equation, ma is going to be mv squared over r, like so. As we'll see starting a little bit later on today, this equation right here is always the opening step when describing the orbit of an object like so in uniform circular motion about another, in this case the planet as it orbits the sun. Okay, now there's always a couple of things that cancel out from this expression, the mass of the planet itself and one of the distances r. And now it just requires me to do one more step here to show in a very simplistic way Kepler's second law. What I'm going to do is just take the square root of both sides and write an expression for the orbital speed of the planet. So in a very simplified form, Kepler's second law in this context appears like so. Now here's what this expression is basically saying. The closer the planet to the sun, the faster it moves, the faster its orbital speed. If you go all the way back to Copernicus, more than 100 years before Newton, remember he made that assumption about planets as they orbit the sun. He assumed that the closer a planet is to the sun, the faster it moves. Now he just made that assumption because it fits what we see in the sky, but now we have a physical reason for it here using the law of universal gravitation. Now remember that Kepler's second law is that rather strange one, the law of equal areas. A planet sweeps out equal areas in equal amounts of time. But basically what that expression is really saying is that the closer a planet is to the sun, the faster it moves. That's what we're seeing here in this very grossly simplified version of Kepler's second law. The orbital speed of the planet depends upon how close it is to the sun. And then we get to Kepler's third law. Here's how we saw it back in our first unit of the year. Remember that Kepler's third law is that simple relationship between two numbers. We saw it in the original unit as p squared equals a cubed, where p was the sidereal period measured in terms of years, and a was the semi-major axis of the orbit in terms of astronomical units. Remember that Kepler discovered his laws empirically by looking at Tycho's data. What I now want to do is use the law of universal gravitation to derive this relationship. When I derive this relationship, however, here's how we're going to see it in this context of chapters 5 and 6. First, the sidereal period. The sidereal period is merely the time necessary for the planet to go from here to here. If you're talking about uniform circular motion, as we are, that's just the period capital T, as we've been referring to, and as such, here in chapters 5 and now 6. And then the right-hand side of the equation, for uniform circular motion, for simplicity, the distance a, that's the same thing as the orbital radius r. So we're going to see Kepler's third law here in chapter 6 in this context. T squared is equal to r cubed. So now what I want to do is derive that expression. In order to derive that expression, we just back up to this step right here in green, and we make a substitution for the speed v. Let me now do the following. The speed v, if you recall from the kinematics of uniform circular motion, is equal to the circumference divided by the period. Watch what happens as I plug that expression for the speed here into the right-hand side of the equation. When I do, however, I have to square all of the terms. So when I do this, I obtain the following. First, the left-hand side, which is this, and then the right-hand side, which is v squared, is equal to this. Notice what I get there in the denominator on the right-hand side. I get a t squared. I get a t squared, like so. So what I'll do next is just take this expression and solve it for t squared, and we'll see what we get. I take the t squared here, and I'm going to move it up to the upper left, and I'm going to cross multiply all of these terms over here to the right-hand side. And when I do, I obtain the following. Like so. Take a look at that carefully. So I just cross-multiplied the terms from my step there on the top board, solving for t squared, and you end up with this. Notice that I end up with t squared is proportional to r cubed. So I'm getting the mathematical form here of Kepler's third law. But as Kepler originally discovered it, he discovered it with an equal sign. T squared is equal to r cubed if t is measured in years, and AU is measured, or excuse me, the distance r is measured in AU. So the question then is this: in those units, what should this number be?
1.
It should be 1. Let's see if it is. Now, the easiest way to show that this is 1 is to actually here algebraically do one more quick step. I'm going to take the r cubed and move it down here to the denominator on the left-hand side, so we can just look at this term here all by itself. And now we get to some numbers. What are some numbers that are in play here? Well, first of all, we have capital G. Remember that capital G is the universal gravitational constant. It's one of nature's fundamental numbers. It describes how gravity works in the universe. I'll tell you towards the end of class, by the way, exactly how it was first measured. But for now, remember what it's equal to. It's this really tiny number, 6.67 times 10 to the minus 11, and then with the rather strange units here in metric SI units, Newton meter squared per kilogram squared. And then the other number that we need is the mass of the sun. How do we know the mass of the sun? Well, in order to know what the mass of the sun is, we need to know one other number, and that's the following. 1 astronomical unit. 1 astronomical unit is about 150 million kilometers. I've said this before. It's 1.5 times 10 to the 11th meters. How do we know that number? Well, it turns out that you have to wait for the right moment, the right celestial alignment, to actually be able to measure an AU in terms of miles or kilometers. The best time at which this could occur is during either what is called a transit of Mercury or a transit of Venus. It's kind of like an eclipse. For example, you stand on the surface of the Earth and you watch Venus as it passes in front of the face of the sun, for example. That's called a transit. So it's not called an eclipse. It's called a transit because Venus, of course, being really small in the sky, is not going to cover up the entire sun. So that's why we refer to it as a transit. This is actually a pretty rare event. Transits of Mercury and transits of Venus, which actually occur in pairs separated by a decade or so for complicated reasons, they only occur a couple of times per century. How many of you, by the way, saw the transit of Venus that occurred just a couple of years ago? I did too. It happened literally right after class at the end of the school day. We were outside in the quad watching it through my filters using my telescopes. That's actually a really rare event. It only happens a couple of times per century. In the mid-18th century, in the 1760s, there were a pair of transits of Venus separated by about 8 years. And it's during those two transits, if you watch the transit from two different locations on the Earth at the exact same time, you could use some parallax to then measure the distance from the Earth to the Sun, 1 AU, in terms of miles or kilometers. This was first done successfully in the mid-18th century. Once we know this number, then you can use, for example, Newtonian gravitation to find the mass of the sun. But you need to know this number first in order to do that. Once we knew this number, we can then find the mass of the sun using Newtonian gravitation. And it's quite big, as you might guess. It's 2 times 10 to the 30th kilograms. So that's ultimately how we know the mass of the sun. We had to make this measurement here first. This measurement here was kind of like a key, if you will, to unlocking all the true numbers associated with the solar system. So now what I'm going to do is take G and the mass of the sun, stick it into here, and let's see what we get. So I'm going to give my calculator a workout here. By the way, we will rapidly discover that the remainder of Chapter 6 gives our calculators a workout. I'm going to first do 4 pi squared. So, and then in the denominator, I first have G, so punching that in appropriately, times the mass of the sun, punching that in as well. And I get a number here that is nowhere near 1. I end up with 2.96 about times 10 to the minus 19. That's nowhere near 1. Well, let's check the units of this thing. We're using metric SI units here in this calculation. So what are the units of this? Well, the units of this are the same as the units of this. That's why I wrote this portion of the expression in the way that I did. This is a time squared divided by a distance cubed. Using metric SI units, it's seconds squared per meter cubed. In other words, I'm in the wrong units. I can't have the time in seconds. I need to have the time in years. I can't have the distance in meters. I need the distance in AU. So what I now have to do is convert. So here's then the conversion. Okay, first of all, the meters to AU. I just erased it a moment ago. But the conversion factor from meters to AU is as follows. 5 times 10 to the 11th meters, quantity cubed, over 1 AU, quantity cubed. Notice how this works. You have meters cubed here, canceling out with meters cubed here, like so. And I'm left with AU cubed in the denominator. And then, lastly, I had to convert the seconds to years. Does anybody remember how many seconds there are in a year? I already mentioned it to you about a week or so ago. Does anybody
Get
remember?
it in 2 seconds.
It's like 3 point.
There's pi times 10 to the 7th. 1 year. It's about 31.5 million seconds. It's 3.15
Is that a
times 10 to the 7 seconds. I'm sorry?
Is that a coincidence?
Yeah, it's just purely a coincidence. It's just an easy way to remember it, pi times 10 to the 7th. Okay, that the pi is just a coincidence. It's about 31.5 million seconds. So now, the second portion of the conversion is now to do this. Multiply by 1 year quantity squared over 3.15 times 10 to the 7th seconds quantity squared, like so. Notice how the units work here. We'll have seconds squared canceling out with seconds squared. Like so. So after I punch out this strange looking number on my calculator and get something, here are now going to be the units. Years squared per AU cubed. So now let's see what we get. So I still have this number here in my calculator, and now the first thing I do is multiply it by 1.5 times 10 to the 11th, raise it to the 3rd power, and then divide that by 3.15 times 10 to the 7th, square that. And even though I've rounded off here a little bit, going out several decimal spaces, the number is 1. So yes, t squared is equal to r cubed if we're in the correct units, time in years, distance in terms of astronomical units. So this second half of the unification that I have done here is basically illustrating that the exact same physical principle that explains motion near the Earth's surface, the end of class last time, and now motion in the sky with respect to planets as they orbit the sun is the exact same thing. The law of universal gravitation explains both. Now, as convincing as these problems are, Newton, however, still has to provide a specific numerical proof that, in fact, his theory of gravity is correct. He does that in Principia in 1687. This is kind of like the last step, if you will, of walking in Newton's footsteps. How do we know exactly whether or not his theory of gravity is correct? Here's what he does.
Have you read Principia? Have you read Principia?
It's written in very old English. I mean, it's 400 years old, basically. So it's very archaic. It's been kind of retranslated into modern English. A very famous edition of that came out just a few years ago. The English physicist Stephen Hawking.
Oh.
He actually sat down with linguists, and they actually converted into modern English, not just, for example, Principia, but also on the revolution of heavenly orbs by Copernicus, and also Ptolemy's Almagest. You could actually read all of those now in modern English if you wanted to. Okay. Here is Newton's proof. We're going to see it as a series of steps.
Are you gonna see the new movie Theory of Everything?
The one about the biopic about Hawking?
Right.
I'll see it eventually. I usually don't go see stuff in theaters because I don't like people. Except you guys.
What if we see it as a class? Field trip.
What
Sorry,
did you?
John?
We could see it as a class.
Nah, that's all right.
Field trip.
Okay, now Newton's proof specifically has to do with the motion of the Earth, or the motion of the moon, excuse me, as it orbits the Earth. Now, as the moon orbits the Earth, it doesn't do so in a perfect circle. It does so in an ellipse. When Newton submitted the proof that we're about to go through, he went through the full-blown calculus involving elliptical orbits. Even if you simplify and just assume that the moon is orbiting the Earth in uniform circular motion, you actually end up with the exact same result anyway. So it is perfectly legitimate for our purposes here to make some simplifications. Okay, now part A of the problem. Part A of the problem is, what does the theory predict? Show that Newtonian gravitation predicts that the moon falls 1/20th of an inch per second. Now, 1/20th of an inch, that's a really tiny distance. That's like the space right here between my finger and my thumb. What we're going to do first is show that Newtonian gravitation predicts that the moon falls this distance in 1 second. And then part B of the problem is, what actually happens? Using the moon's orbital data, which we've known at least since the time of Ptolemy, for example, show that observations match the theoretical prediction. In other words, show that Newton's theory of gravitation is correct. So this is the specific numerical proof that he submitted in Principia, demonstrating that his theory is correct. Okay, now how do we even think of the moon as falling? Well, I actually briefly went through this at the beginning of chapter 4 when I gave you my qualitative description of Newton's laws of motion. If you remember, I basically drew out the following scenario. Okay, let's say that right here is the Earth, and just conceptually, you take an object and you throw it near the Earth's surface, it behaves as a projectile, it falls to the ground. If you throw it a little bit harder, it travels a greater distance, falls to the ground. But remember, if you throw it hard enough, as the object falls, it ends up falling around the Earth forever. The Earth's surface curves away from it like so. The object ends up in orbit. Newton himself actually literally drew this diagram in Principia and then used it just in a conceptual way of how we can understand that motion near the Earth's surface with a projectile and motion in the heavens, in this case the moon orbiting the Earth, is the same thing. So yeah, we're going to think of the moon as a projectile in this calculation. There is, however, a complication as I begin this process. The complication is that Newton didn't know the value of capital G, the universal gravitational constant. That actually wasn't measured until later on. So how does he get around this problem of not knowing capital G? He basically sets up a ratio. Here's what he does. So part A here is the theoretical prediction. And we break this up basically into two parts. The first thing that we do is we calculate how far an object will fall in a time, we'll say small t of 1 second, if dropped from rest near the Earth's surface. As you'll see in a little bit, this is the first part of this ratio that Newton is going to be setting up here for us. Okay, now this calculation, it turns out, is actually what I did basically at the end of class last time. If you remember at the end of class last time, we did the following. Okay, we have first of all the Earth. Remember that mathematically we treat the entire mass of the Earth as a point at its geometric center. This was a result of a three-dimensional calculation that Newton himself performed. Okay, and then we have an object here of mass m in free fall near the surface of the Earth. Let's go ahead and think of it as an apple. And now, the two objects here, as long as we're near the surface of the Earth, they're separated by a distance that's basically just equal to the radius of the Earth itself. So right here is the radius of the Earth. And now we just set up a little bit of F equals ma. Once again, according to Newton, there's only one force acting on the apple, and that's the force of gravity. So the force of gravity is capital G times the mass of the Earth times the mass of the apple divided by the distance between the 2 points squared divided by the radius of the Earth squared. And then this is equal to mass times acceleration, where the acceleration is small g, acceleration due to gravity, and we end up with the result that we saw at the end of class last time. Small g is equal to this number here. Now remember, of course, that small g was known at the time. It was measured 50 years earlier by Galileo. This is, however, an English units problem. That's originally how Newton did his work. So we have to think of small g here as 32 feet per second squared. And now, let's just calculate the distance that an object will fall in 1 second if you drop it from rest. This is just a little bit of basic free fall kinematics like we saw it back at the beginning of chapter 2. Let's call the distance that an object falls small d. If you drop it from rest, ignoring negative signs, the distance that it falls is just a 1/2 gt squared term. So in 1 second, then, an object is going to fall the following distance. 1/2 times 32 times 1 squared, which is a total of 16 feet. Okay, now we go to the moon. And now we set up the following calculation. Now we're going to calculate how far the moon falls in time t equal to 1 second. And then once again, this is what most introductory students have trouble wrapping their head around. How can you think of the moon as falling? Think of it like this. So right here we'll say is the moon's orbit about the Earth. So we have the Earth right here, mass m sub e. Let's say the moon is right here in my diagram. It has a mass, we'll call it m moon. The 2 points here are separated by some distance. Let's refer to it as small r. Okay, now if I assume that the moon here on my diagram is orbiting, say, clockwise, that means that at this moment it's moving in this direction like so. And now think of the moon as a projectile. And think all the way back to chapter 3 when I did the monkey hunter demonstration. Remember how I said to picture a projectile? Picture it as falling, but falling below a line that it would have traveled if there was no acceleration. Now remember how I set up that demonstration. I had my gun over there on the third desk. It was pointed directly at the target, if you remember, up on the ceiling. If the projectile didn't fall, it just would have moved along that line and hit the target. But a projectile is falling. It's falling below that line. So if you think of the moon as a projectile, if it didn't fall, it would move in this direction. But it does fall. It's falling below that line. We want to calculate how far it's going to fall below that line in 1 second. That's the basic idea here. Okay, now what we do is we apply the force of gravity here. So we have only one force exerted upon the moon. That's gravity. That is then therefore going to give us an acceleration in this direction. Let's just refer to that as a moon. So now here's what F equals ma looks like for this. So we have the force of gravity applied to the moon due to the Earth. That's this here. Equals then the mass of the moon multiplied by its acceleration. So mass of the moon cancels out. And then the acceleration of the moon is this. And then using this acceleration, whatever it's equal to, we'll see what it's equal to in just a few minutes. The distance that the moon will fall below this line is the same formula as this above, but it's now, instead of small g, the acceleration of the moon. Think of the moon as like a projectile that's being fired here horizontally on my diagram. And then therefore, the projectile falls below that line. The distance that it falls vertically below that line is basically 1/2 at squared. So the distance that the moon will fall, we'll call it d moon, is 1/2 times the acceleration of the moon times t squared, where small t is once again 1 second. Okay, how do we find the acceleration of the moon if we don't know g and we don't know the mass of the Earth? Here's where the ratio comes in. It has to do specifically with, on my lower board diagram, small r. Small r, remember, is the distance from the Earth to the moon. We've known that distance since the time of Ptolemy, more than 2,000 years ago. Does anybody remember what Ptolemy's result was the distance from the Earth to the moon. I actually had you guys model it, if you remember, on the desk by using clay balls. And the distance from the Earth to the moon was some number of Earth radii. Does anybody remember what it was?
60?
60, that's right. Numbers, by the way, in this class sometimes come back to haunt you. This is why that number is so important. As measured by Ptolemy, the distance from the Earth to the moon is 60 Earth radii. So what I'm going to do to find the acceleration of the moon here is I'm going to replace the small r with 60 Earth radii. That will give me this. Take a look at this carefully. Now 60 squared there in a denominator is 3,600. So I get this. So. And then this right here from the top board is small g. So in other words, the acceleration of the moon is 1/3600th of g. The easiest way to think about this is that in a very detailed way, all that I have basically said is this. You stand at the surface of the Earth, you measure small g, that's the top board, 32 feet per second squared. And then you go 60 times further away from the center of the Earth than the surface of the Earth. If gravity is an inverse square law, then the acceleration due to gravity should be 1/60 squared, its value here at the surface of the Earth. And it is. The acceleration due to gravity at the location of the moon is 1/60 squared, the value of acceleration due to gravity here at the surface of the Earth. So if you go 60 times further away, gravity is 1/60 squared times as weak. That's the easiest way to think of what it is that I just did here. It took me about 10 minutes, however, to go through that. Yes?
I don't understand how G and then the mass of the Earth divided by the radius.
Okay, so
G.
you've got gm over r squared, where little r is 60 times the Earth's radius, okay? So in other words, at the location of the moon, we're 60 times further away from the center of the Earth than the surface of the Earth is. So if gravity is an inverse square law, then it should be weaker by a factor of 1/60 squared. And it is. It's 1/3600th the value as it is here at the surface of the Earth. That's the easiest way to think of this calculation. So because he didn't know what capital G was and he didn't know what the mass of the Earth was, what he's basically doing here is making a comparison with a number that we already do know, and that's small g, 32 feet per second squared. So now, if you take this expression for the acceleration of the moon, which is this, and stick it in here, then according to the theory, the distance that the moon will fall is 1/3600th of 1/2 gt squared. Take a look at that carefully. All that I did was I replaced the acceleration of the moon with 1/3600th of g. That gave me this. And remember that from the top board here in parentheses, this was 16 feet. So this is 1/3600th of 16 feet. So according to the theory, the distance that the moon falls below this line in 1 second is 16 feet divided by 3,600. And then as he originally wrote it in Principia, he converted to inches. So I'm going to take the amount of feet that I have here in my calculator and multiply it by 12 inches per foot. And you end up with the following number. It's 0.05 inches. That's 1/20th of an inch. So according to the theory, the moon falls in 1 second, 1/20th of an inch. So now part B is what actually happens. In order to calculate what actually happens, we only need to know two numbers, and using those two numbers, we construct a right triangle. It just looks like this. You're walking in Newton's footsteps. You're seeing his genius at work. This is the reason why we put him on a pedestal. Now part B, what actually happens? Okay, well, as I said, we just need two numbers to show what actually happens, and both of these numbers have been known since the time of at least Ptolemy. And using these two numbers, we're just going to construct a right triangle. Here's how it works. Okay, the first number is just the distance from the Earth to the Moon. Remember this distance we referred to earlier as small r. Small r, once again, is 60 Earth radii. However, of course, Newton does the calculation here in terms of inches. So how many inches is 60 Earth radii? Well, it's a lot. I've got it written down. It's 151,338,52800 inches. So just in case you're curious, that's the distance from the Earth to the Moon in terms of inches. And then the other number that we need is the Moon's, not its synodic period, but its true period, its sidereal period. How long it takes the Moon to go from here to here. Now remember when we see the lunar phases, like from full to full, that's with respect to our moving platform. That's a synodic period. Remember, that's about 29 days and change. That's how we get the calendar months, blah, 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 like we talked about back in the first unit. That's not really the Moon's true period, though. The Moon's true period, in other words, how gravity works, which is what we're doing here, is its sidereal period, the time that it takes to go from here to here, 360 degrees on this circle. The sidereal period of the Moon is a little bit less than 29 days. It's like about 27 1/3 days or so. In terms of seconds, 27 1/3 days, I've got that number written down as well. That's 2,360,590 seconds. No, 360,590 seconds. Like so. Just using these two numbers, which we've known since the time of Ptolemy, just in modern measurements. Using these two numbers now, we can calculate how far the Moon falls in 1 second. Now, how do I get this triangle? Well, I've got one side of the triangle already. The other side of the triangle is going to be right here. Now, if we picture the Moon as being right here in my diagram, remember like from earlier, if the Moon is orbiting the Earth here clockwise, it would move in this direction like so if it wasn't falling. Let's calculate how big this distance is in 1 second. In other words, this is literally the linear distance that the Moon moves in 1 second. Let's call this distance here S. And how do we find that distance? Well, that distance is going to equal the speed of the Moon multiplied by the time small t of 1 second, where the speed of the Moon is its circumference divided by its sidereal period. So let's calculate this number here. So this is the linear distance that the Moon moves in 1 second in terms of inches, just in case you were curious. So what's it equal to? Well, first of all, we have 2 times pi times this ginormous number right here, 151,338,52800, and then divided by the sidereal period, 2,360,590. And this comes out to be about 40,282 inches. See, so now you know how far the Moon moves in 1 second in terms of inches. It's 40,282 inches. And then, the hypotenuse on the triangle is right here. Now, what is the hypotenuse of the triangle? It's the sum of 2 numbers. First of all, right here between my fingers, that's once again small r. Like so. And then this right here is our unknown. This is the distance that the Moon falls below this line in 1 second. This right here is our d Moon. And then the last step is just to set up Pythagorean theorem and solve for d Moon. Before I do, Sean, you had a hand up before we go.
Is all for S, is that 40,282 inches per sidereal period?
No, this is per second. That's how far the Moon moves, is a linear stretched out distance, if you will. This green line right here, in 1 second, is 40,282 inches. So that's an interesting little trivia question to now know the answer to. Okay. Okay, now at this point, I just set up Pythagorean theorem. So now my Pythagorean theorem is going to look like the following. We first of all have, from the board above, r squared plus s squared equals the hypotenuse squared. The hypotenuse, however, is the sum of r and our unknown d moon. And now I just solve for d moon. In order to solve for d moon, I have to FOIL, or whatever the heck it is they call it, this side of the equation. When you FOIL this side of the equation, let's see, you get this. So I just FOILed the right-hand side, multiplied it by itself. And then, as I said, it's just solve for d moon. We could actually simplify what I have here that's left over at this point. Take a look at the d moon squared. Remember what d moon is predicted to be. It's only predicted to be tiny, 1/20th of an inch. So d moon squared is even smaller still. It's like 1/400. How big is d moon squared compared to r, the diagram above, and s? It's tiny, it's negligible. So because it's negligible, all I have to do is now solve for this guy right here. So at this point, I'm just going to cancel out the r squared from either side. They drop. And now just divide the 2r over here to the left-hand side to finally get d moon. So the actual distance that the moon falls below that green line there, up on the top board, in 1 second, is the following. So I still have the s here in my calculator, so I'm going to square it. And then divided by 2 times that big number there up on the top board. 2 times 151,338,52800. And sure enough, it's 0.05 inches. It's 1/20th of an inch. The fact that this 1/20th of an inch, what actually happens, matches up with this 1/20th of an inch, what the theory predicts. What does that tell you about Newton's theory of gravitation? It tells you, of course, that it's correct. And now because all of you here, including myself, are in the presence here of the long-dead master, you must still, however, show your proper respect for exactly what it was that Isaac Newton did almost 400 years ago. So yes, Newton's theory of gravity is correct. Before we go any further, however, think about exactly what Newton's theory of gravity is saying. If you think about it carefully, it looks and smells like magic. Because basically what Newton is saying is this. Imagine, for example, you've got the sun and the earth. They're separated by 150 million kilometers of completely empty space. There's nothing there. It's a vacuum. And yet somehow, instantaneously, almost magically, if you will, the sun is able to reach across that 150 million kilometers of completely empty space and somehow grab a hold of the earth with a force and hold it such that the earth then orbits the sun. To Newton and his contemporaries, that looked and smelled like magic. One of the purposes of the Enlightenment, of the scientific revolution, which is really embodied here in Isaac Newton, was basically to cast forever out of the study of the natural world, religion, and the occult. And what does Newton do? He introduces into science his theory of gravity, which frankly looks and smells like magic. And Newton was well aware of this. Newton's defense of his theory was simply this. Regardless of how gravity may really act in a fundamental way, it obeys these mathematical laws. And it makes testable predictions. And it passes those tests every single time, such as this one right here that I've been outlining for the last 20 minutes in class. There's a very famous quote attributed to Newton in this context. He said basically, I feign no hypothesis. In other words, he doesn't go any further than this. Regardless of what gravity may be at a more fundamental level, it works this way mathematically. And it makes testable predictions, and it passes those tests every single time. So you can think of Isaac Newton as the person, yes, who invented physics. His theory of gravity, of course, ties everything together. But it's not a complete explanation of gravity. It shows us how it behaves mathematically, but it really doesn't say anything more than that. So yeah, Newton invented physics. But then 250 years later, somebody else came along and reinvented physics. Who was that person?
Albert
That was Albert Einstein. And exactly what it was that he did with gravity, well, we'll get to that a little bit later on. Let's take a short break.
I was definitely going to say that's bad. And then no, that's only on those. That's only on some TV shows. It tends to TV shows. I think on SpongeBob there is that. Remember the mermaid dog one where he was favorite?
Newton really was the right guy.
Like,
at the right
stronger
time.
than down.
Oh,
That
he
was
was
magic.
what?
He really was the right guy at the right time.
Where do you think the Apple story came
The Apple story is considered somewhat apocryphal. You know what that means? It's kind of like a legend.
from? Right.
He later recounted to a friend of his later on in life that he got the idea of treating gravity as a force, kind of like his eureka moment that led him down the path of this calculation, for example. When he was sitting at his family farm, he was sitting out in one of the apple fields, and he saw an apple fall from a tree. While he was looking at the tree, he could also see in the background the moon in the sky. And that was kind of like his flash of insight. And maybe it's the same thing. What's holding the moon in its orbit is the same thing as what causes the apple to fall from the tree. So it's kind of a scientific legend, if you will. The story is kind of considered apocryphal.
So it didn't actually hit him on the head.
No, it probably didn't actually hit him on the head. There's kind of a very famous, very funny Far Side cartoon. I think I've got it somewhere here in the room, where there's a bunch of guys sitting around in an apple orchard, and they're all drawing on their notebooks, and they're like, I don't have any ideas yet. Do you have any ideas, Newton? And Newton's sitting under a tree, and there's this gigantic apple above him, about to fall onto his head. So whether or not it actually hit him on the head, you know, probably not. But he later recounted the story to a friend of his that he got the idea when he saw an apple fall, while he could also see in the same field of vision the moon in the sky. Sometimes it literally is like that. Sometimes there's just the right moment, right person at the right time, that's the right idea. Yeah. I mean, there's numerous instances like this littered throughout scientific history. Newton's, of course, is one of the most famous examples of it. I mean, it's hard to believe, but Newton literally intuited the equation G(m)(m) over r squared. He intuited the relationship F equals ma. He basically realized this is the way it has to work.
So he didn't
Einstein did similar things as well. He basically said, this is the way it has to work.
So he didn't derive anything.
No, well, he didn't derive it in this sense. He recognized the existence of these fundamental expressions. And then from the expressions, then you could like derive Kepler's laws, for example. One of the things that introductory physics students have to do, using the full-blown calculus, is derive all of Kepler's laws using the law of universal gravitation. The law of universal gravitation doesn't just predict that the planetary orbits are ellipses. It actually predicts that the path that is followed by an object under the influence of gravity always traces out a conic section. It's just one of those conic sections happens to be the ellipse. The other conic sections occur as well, parabolas, hyperbolas, and circles. And you see this directly from the relationships when you do the calculus. And when you see it for the first time, you're like, Jesus Christ. See how it all works. All right, let me go ahead and move on. There's one more basic thing that we have to get to before we start to take a look at applications for the remainder of the chapter. And when it gets to the applications in a little while, by the way, the law of universal gravitation truly is a universal law. So we can apply it throughout the entire universe. So after I get through the remainder of the basics here in just a few moments, when I start to apply the law of universal gravitation to situations in the universe as a whole, this is my opportunity to throw as much astronomy at you as I possibly can. So that's what we'll be doing after we get through the remainder here of the basics themselves. The last little bit of the basics here is just to understand briefly exactly how capital G was first measured. So I'm going to give you a description of the experiment that was performed first to measure capital G. And then I actually have a short film clip of the experiment itself that I'll show you in just a few minutes. Yes, the president's again. Okay, now the first successful measurement of capital G, the experiment that does it, is named after the person who first performed the experiment. It's called the Cavendish experiment. Cavendish experiment actually wasn't performed until the 1790s. So this is actually well after Isaac Newton's death. Isaac Newton died, I believe it was, in 1732. So it was actually more than 50 years after Newton's death when we finally measured capital G. Capital G is measured by using a very specific type of pendulum. What Cavendish did was the following. He first of all took a long wire, and then hanging from the wire was a long iron bar like so. It was like 10 feet long, something like that. And then on either side of the pendulum, here and here, he had masses, called them M, they're identical to each other, attached. Okay, and then on the floor below, he had two other stationary masses that were identical. I'll call them capital M here, capital M here. This specific type of pendulum, by the way, which can swivel like this in the horizontal plane on my diagram, this is referred to as a torsional pendulum. Now this is what the setup looks like when you look at it from the side. But when you look at it from the top view, it looks like this. So now here's the pendulum as seen from above, where here are the two masses M, like so. And then the center, where the wire is, that's like this. And the wire is perpendicular to us like this. And then the masses on the floor off to the side are positioned in the following way. Capital M is positioned here first, and it's positioned such that it's closer to this side of the pendulum than to this side. And then the other capital M on the other side of the diagram above, that's positioned here. And it's positioned such that it's closer to this side of the pendulum than to this side. And then if you just let the pendulum go, what happens? Well, there is a very minute force of gravity exerted upon this end of the pendulum due to this mass here. There is a very minute force of gravity exerted on this side of the pendulum in this direction due to this mass here. And then literally what happens, and I've seen it happen myself because I've performed the experiment, is that the pendulum does the following. Very slowly swivels in this direction, overshoots the masses, slows down and stops, turns around, moves in the opposite direction, overshoots the masses, slows down and stops, and it does this repeatedly over and over. It oscillates. But as it oscillates, its amplitude of oscillation gets less and less and less. It eventually ends up, after several hours, like this. The pendulum executes a very specific type of motion. It's called damped harmonic motion. Damped harmonic motion, which we'll, by the way, take a look at briefly in the second semester, was very well understood in the time of Cavendish. By examining the details of the motion, that tells you how much force is exerted upon the pendulum itself. So the amount of force exerted upon the pendulum comes from the details of the damped harmonic motion. Okay, now just take a look at the basics of the equation itself. The motion of the pendulum, the details of that motion, that tells you how much force was exerted upon the pendulum. So in other words, we know what this number is. It's basically measured. And then take a look at the right-hand side. On the right-hand side of the expression, you know all of the relevant masses, their experimental controls. You know all of the relevant distances, their experimental controls. So all of this stuff over here is known. Their experimental controls. So if the motion of the pendulum itself gives you the force, and everything on the right-hand side of the equation except for capital G is known, then therefore, of course, you could measure capital G. That's the basic idea. Now the experiment, however, itself is very difficult to pull off as Cavendish originally devised. The reason for that, of course, is because capital G is so small. The amount of gravity that's exerted upon this pendulum due to the object sitting off to the side is next to nothing. So the motion itself literally takes place over the course of several hours. And I know because I've seen and I've done the experiment for myself. When you major in one of the scientific disciplines in college, one of the classes that you have to take is usually some version of what is called advanced laboratory. And what you have to do in that class, it's either a year long, in some cases it's 2 years long, is you have to repeat all of the classic experiments that have been done in your discipline up until that point. So as a physics major, we had to do the Cavendish experiment. Unlike you guys, however, in this class, we had to get less than 1% error. Otherwise, we failed the experiment. So they actually had us in this class perform the Cavendish experiment twice. And we were, by the way, given as much time as we needed to actually do the experiment over the course of a semester. It was just get it done by the end of the semester. So we had weeks to do it if necessary while doing other experiments as well. So when we first did the Cavendish experiment, they set it up for us in this manner where it was done on a large scale. And it's kind of eerie because you can't see the pendulum itself moving in real time because it's moving so slowly. It's like, you know, watching the hour hand on a clock or something like that. It's moving, but it's moving so slowly, the human eye is not going to notice it. We also discovered, as Cavendish himself originally discovered, that the mere act of walking in the room while the motion is occurring is enough to throw off the motion because it's so slight. So the vibration of your footsteps was enough to disturb the pendulum. Just the air currents of you walking through the room is enough to disturb the pendulum. And so we discovered all of this over the course of several tries in doing the experiment. So finally what we had to do was get it set up as is described here, and then what we did is we retreated to a side office. And that side office had a plate glass window, and so we just sat in the office for several hours while the motion was occurring, periodically making our measurements as we went. When we did this, however, you can't see the pendulum moving in real time, it's too slow. So we would just sit there in the office, we'd look at the pendulum, note its position, and then we would look at our papers and, you know, work on homework problems for 10 minutes. And then we would look up again, and the pendulum had moved. And then we would look at our papers and work on our homework problems for 10 minutes. Look up again, and the pendulum had moved. It's kind of like that scene in The Shining. There's this scene in The Shining where the character is being chased by the animals that are cut into the bushes, and he can't see the bushes moving, but every time he looks up, the bushes are getting closer and closer to him. Those of you that have read the book may be familiar with this scene. It's kind of like that. You would look up, and the pendulum's changed position. Look up again, and it's changed position. And it's so slow, you can't see it moving in real time. That's how they had us do the experiment the first time. It was very difficult to pull off. However, if you do it on a small scale, it's actually pretty easy to do. And that's what they show here in this film. So let's take a look at that. All right, now here's how I'm going to have to set this up. I'm not going to cast it on the screen because then I got to turn my projector off and all that crap. So instead I'm going to do this. Yes, the ex-presidents actually performed the experiment for us.
Which ones?
Well, it's JFK and Dwight Eisenhower, presumably, but in this case we can't see their faces. We can only see their hands.
Yeah, you gotta say.
Here's what I'm going to
Oh, maybe. I doubt it.
do. Let me get rid of this. I'm going to use the top board here as a screen. This is as old school as it gets. Speaking of old school experiments, 1790 playing around with magnetic pendulum in a lab room. Don't walk in the room, you're screwing up my experiment. And here we go. So, the measurement of capital G. So when they filmed this version of the experiment, it's done on a small scale. This is how we did it with our second attempt, if you will. If you do it in this manner, it's actually fairly easy to do. What they do here is they encase their pendulum in a small box, and you then actually just take the air out of the box, so it's in a vacuum chamber. Okay, now, as they close up here, as they show us a close-up of their pendulum itself, you can see how a light is shining onto a mirror here on the pendulum. And then in the distance, you see that meter stick? Well, the reflection is cast onto that meter stick. This is how, in this version of the experiment, they know what the position of their pendulum is. So that's how they're making their measurements here. Okay, now you have to get the experiment set up first. The way that you do that is you take, in this case, large lead balls, and you place them diagonally across from each other on either side of the pendulum box. So one of the presidents reaches in, and he positions the lead balls like so. Okay, then over the course of several hours, the pendulum is going to oscillate and then it's going to line up with those balls. That's when the experiment starts. That's the initial position of the pendulum. And then what they'll do here in just a moment is they'll reverse the position of the large lead balls. And then the pendulum will oscillate to its new equilibrium position. They photographed this for us using the reflection on the meter stick. They photographed this for us at 80 times normal speed. So this is all not to the naked eye. This is photographed at 80 times normal speed. Okay, so now they shift the balls here. They'll show us them doing this. Come on. Like so. Come on. Like that. Don't touch the box. And now they photograph the oscillating pendulum just using the reflection onto the meter stick in the background. They photograph it at 80 times normal speed. And then the damped harmonic motion occurs. Like so. So yeah, it's the force of gravity exerted on the pendulum from the large lead balls that's causing this. Now, damped harmonic motion has a very characteristic graph associated with it. What you're seeing here horizontally is the position of the pendulum as a function of time vertically downwards like so. Notice that the amplitude of the oscillation is decreasing as time goes on, and eventually the pendulum reaches its new equilibrium position lined up with the large lead balls. Those of you that are close will see there the numbers on the time axis going downwards into terms of thousands of seconds. So yeah, you're talking about several hours here for the motion to occur, and it's during this motion that you can't, of course, disturb the pendulum whatsoever. Now, when you do the experiment like this on a small scale and you take the air out of the box and blah, 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 it's actually fairly easy to do. I think it only took us a single afternoon to actually get a really good result the first time that we tried this with this second version of the experiment. The hard part was doing it originally as Cavendish did with this gigantic pendulum in this room, which would be extremely difficult to do in retrospect. Okay, now there's no fast forwarding button here, so I have to let this finish. But basically, the details of that graph there, that tells you how much force was exerted upon the pendulum through the calculations. And then from that, in the equation m over r squared, everything else is an experimental control except for capital G, of course, and that is then what you measure. So that's the basic idea of the Cavendish experiment. It uses basically a pendulum to find it. But because G is so small, it's difficult to do, as you can see. And let this finish. Yeah. Credits roll. I don't think there's a credit card either. Yeah. All right, good. All right, so that's the Cavendish experiment. Watch out, here come the lights. And now at this point, it's application. Henry, before I do.
When you performed your experiment, you didn't have a vacuum room or anything, did you?
No. It was, so that's why he had to do a Cavendish originally on a large scale with this heavy pendulum,
Okay.
and huge masses off to the side, because he couldn't get rid of the air in the room. Nowadays, of course, you can with vacuum pumps. You can do it on a small scale, as was depicted in the film. Do it that way; it's actually fairly easy to do.
And
Okay?
if there are any other objects in the room, would that?
As long as they're far away, the inverse square law means that the force of gravity exerted upon your pendulum due to other objects in the room drops down very rapidly. So yeah, I mean, we have cleared the immediate area, and that's why you use large, dense masses, iron weights or lead balls in this case. Jenna?
First time you did it, did you like walk around in the air currents and you found out after
Yeah, we
3
just started
hours?
very, wait a second.
After 3 hours.
This is not working.
That's
Yeah, we had to eliminate those sources of error. So unlike you guys, where I basically tell you everything to do in a lab exercise, they just say, there it is, go do it. So if you major in biology, how many of you are thinking about doing that? Maybe pre-med, something like that? If you major in biology and you take a similar class, and you will have to in some manner, they will say, okay, do the Miller-Urey experiment. And they'll hand you the glass bulb. Here's your vacuum source. Here's your stuff to turn into amino acids. Go do it. And they'll say, do it in 2 hours. That's it. So yeah, that's what happens when you end up majoring in the sciences. You got to do all the experiments yourself. Okay? All right. Now at this point, we start to look at some applications. Let's start off something relatively simple and straightforward. So let's try to follow. As we start to move outwards from the Earth here, we'll start very simply. Let's describe what happens when you have an artificial satellite orbiting the Earth. We'll just keep it orbiting the Earth, however, in uniform circular motion to keep things easy. How many of you saw the movie Gravity from about a year or two ago? It's an okay film. They get some things right, they get some things wrong. We'll see some of that here in this problem. No, I've not yet seen Interstellar.
It's really good.
That's what I've heard. I'm not sure if I'll have a chance to see it anytime soon. Maybe over the holidays if it's still around.
Too many concerts.
I've got a lot of other stuff going on outside right now.
A lot of concerts coming out.
Just like with you guys, my life is crazy too.
Sean, like kids?
Oh, no. Why would I have kids? I don't even want friends. I don't want kids. All right, now it says derive an expression for the period of an artificial satellite orbiting the Earth in uniform circular motion. Okay, that first sentence there is basically just a repeat, as we'll see, of Kepler's third law. Kepler's laws don't just apply to planets orbiting the sun, they also apply to any object orbiting any other object, such as, for example, an artificial satellite orbiting the Earth. And then we'll take a look at two number problems associated with our basic expression. We'll see what happens if you have an object orbit the Earth at an altitude of only 1 meter above the ground. That is possible, provided you go fast enough, as we'll see. And at the very end, we'll also take a look at another application as well, something called a geosynchronous satellite.
That's just a problem.
It's just a continuation of the general thing that we're going to do in the first sentence. The first sentence is just a general expression. As you'll see, it's just a repeat here of Kepler's third law, and then we'll apply it to a couple of simple situations. Okay, so here's then how we begin to picture such a situation. So here's the Earth. Right here we'll say, once again, is the mass of the Earth. And then here's a satellite like so, in uniform circular motion about the Earth at some altitude above the ground. The satellite itself has mass m. Now, just like I did earlier when setting up at the beginning of the period today, Kepler's laws of planetary motion, our opening step here in describing an orbit always looks exactly the same. We have, first of all, the two objects here, the satellite and the center of the Earth, separated by some distance, small r. And then we only have one force exerted upon the satellite, that's the force of gravity, and it causes, in this case, a centripetal acceleration inwards towards the center of the Earth, the center of this orbital circle, like so. And now we just set up F equals ma. So we have the force of gravity between the 2 points, gmm over r squared, equals then the mass times acceleration, mv squared over r. So this was our opening step early on for Kepler's laws today. Same thing here. Same things always cancel out. The mass m cancels, as does one of the distances r. And then it says in the problem that we're trying to come up with an expression for the period. So just like I did for Kepler's third law at the beginning of the period today, we make the following substitution. Speed v is circumference divided by period. We plug that into here, and we have to square each of the terms. So cleaning up the expression that I have thus far, here on the left-hand side, we first of all have this, and then on the right-hand side, we have the following. And now I'm just going to solve here for t squared, and we're going to see Kepler's third law once again. So I'm just going to cross multiply the stuff here in solving for t squared. And now in the context of a satellite orbiting the Earth, Kepler's third law looks like this. Like so. So there's the t squared is proportional to r cubed relationship. Once again, we're just applying it here a little bit differently in this problem with an artificial satellite that is orbiting the Earth. Okay, now what we need to do is apply this general expression, once I take the square root of it, to the situations here that are being described. Okay, first of all, let me go ahead and take the square root of this to get the period by itself. That then gives us this expression here. And now, how could it be that you could have an object orbit the Earth, be in free fall around the Earth forever and not hit the ground when it's only an altitude of 1 meter above the ground, like this distance here? Let's just visualize this very simply. Let's assume there's no atmosphere for your satellite to burn up in. Let's assume there's no mountains or buildings in the way for it to run into. So you've got a perfectly featureless spherical Earth with no atmosphere. Is it possible to have an object orbit the Earth at an altitude of only 1 meter above the ground? Yes, provided you go fast enough. So now what I'm going to do here to find that period is I'm going to set r here equal to the radius of the Earth. In other words, I'm going to say that the small r up here in my diagram is just the radius of the Earth itself. For all practical purposes, that is the radius of this circle if you're only 1 meter above the ground. So now let's see what happens if I set r equal to the radius of the Earth. The orbital period of the satellite then would have to be the following. And now we have these various numbers that will appear in this problem and in subsequent problems. You don't have to memorize any of these numbers or anything like that. They're always given quantities. So from earlier, we now know, as measured from the Cavendish experiment, that capital G is this number. Okay, the mass of the Earth. I mentioned this at the end of class last time. The mass of the Earth is 6 times 10 to the 24 kilograms. And then lastly here, the radius of the Earth. This goes all the way back to Eratosthenes. The radius of the Earth, 6,400 kilometers, is about 6.4 times 10 to the 6 meters. So all of these numbers are known. They're all givens. I'm just going to plug them in here. When I plug them in here, I'm calculating how long it takes in seconds for this satellite to go around the Earth. If it's orbiting, it's basically at the Earth's surface. So, punching it out. Once again, we're giving our calculators here a workout. First of all, 4 times pi squared times the radius of the Earth cubed. Divide that by G times the mass of the Earth. Square root all of that junk. And in terms of seconds, it's about 5,085 seconds. That's a little bit under 2 hours. If I divide that by 3,600 seconds in an hour, it's a number we've seen before. It's 1.4 hours. Does anybody remember from just about maybe a week or so ago where we saw that number previously in chapter 5? We had a problem in chapter 5 where we spun the Earth, remember, faster and faster and faster, such that if you spin it fast enough, everybody becomes a projectile at the Earth's equator, and you end up in orbit around the Earth. That's what's happening here. You're in orbit. When we saw it back in chapter 5, we saw it as the rotational period of the Earth, my left hand, being the same as the orbital period of a person close to the ground. That person is orbiting the Earth while the Earth rotates with them. That's essentially the same situation here. So if I took this marker and I threw it fast enough such that it would orbit the Earth in a time of about 85 minutes or so, it would actually never fall to the ground. Now, it would be moving pretty fast, however, in this case. Let me go ahead and calculate its speed. The speed of this object here relative to the center of the Earth, not the surface of the Earth, the center of the Earth would be the circumference of that orbital circle divided by that period of 5,085 seconds. So what is this number here? It's pretty big. So that number is 2 times pi times the radius of the Earth divided by the period of 5,085 seconds. And it comes out to be about 7908 or so meters per second. That's just under 8 kilometers per second. So if I took this marker and threw it, such that I gave it a speed of about 8 kilometers per second, technically it's in orbit.
What's that in miles per hour?
In miles per hour, it's like 17,000 plus miles per hour, something like that. So if I took the marker and threw it that fast, it would be in orbit. Now, what happens when you do have satellites orbit the Earth in what is called low Earth orbit? Low Earth orbit, which is like where the space shuttle used to operate, and also the space station, for example, that's a few hundred miles above the surface of the Earth. What happens to the orbital period as you get further and further away from the surface of the Earth. As the R on my diagram above gets bigger,
It increases.
it gets a little bigger, okay? If you go up into low Earth orbit, which is a few hundred miles above the surface of the Earth, it takes about 90 minutes or so, a little bit more than this. It takes about 90 minutes or so for a satellite to orbit the Earth. That's typical for an orbit at a low altitude of just a few hundred miles. Now, how many of you, once again, saw the movie Gravity a few years ago? It got a couple of things right. One of the things that it did get right, if you remember in the film, is the time between hitting the debris orbit per orbit that causes the whole accident in the movie and blah, blah, blah. Well, if it takes 90 minutes or so to go all the way around the Earth, and you're going in one direction and the debris is going in the opposite direction, how often are you going to hit the debris? Every 45 minutes when you pass through it, for example, on the other side of the Earth. They actually got that right in the film. The time between hitting the debris from one interval to the next was about 45 minutes, as depicted in the film. They got that right. What they got wrong, however, was the following. There is no way that you would be able to see the debris coming at you as they show you in the movie. In the movie, they have scenes with Sandra Bullock, and she looks out in the distance in her spacesuit, and you see this debris field coming at her like this, and it starts shredding up the spacecraft and blah, blah, blah. The reason why you would never see it is because the relative speed between you and the debris would be huge. If you're going at 8 kilometers per second in this direction, and the debris is going at 8 kilometers per second in this direction, opposite of you, what is the relative speed of the debris according to you? It's 16 kilometers per second. There's no way you're going to see it coming. I mean, it's on you in a blink of an eye, and it basically goes right through you. So in that portion of the film, when she sees the debris coming at her, the relative speed is 16 kilometers per second. There's no way you're ever going to see it coming. I didn't like the end of that movie, by the way. At the end of the movie, she crawls out of the lake, and that's basically the end of the movie. I thought a much better ending was she crawls out of the lake, and there's apes on horseback carrying rifles next to her. That would have been a lot better. She ends up on the planet of the apes instead. That would have been great.
That would have been great.
Now, let's take a look at the very bottom of the problem. How many of you have satellite TV, direct TV or Dish Network, for example? A couple of you have. Do you ever have to go outside at different times of the day or at different times of the year and reposition your satellite dish such that you can receive the television signal? No, absolutely not. Your satellite dish is always pointed at the satellite in the sky. It's always pointed at the same position in the sky. So in other words, relative to the Earth's surface, the satellite is at the same position in the sky 24 hours per day. So then therefore, is the satellite orbiting the Earth?
No.
Yes, it is, but in a very specific way, what is called a geosynchronous orbit. The easiest way to picture a geosynchronous orbit is to take my orbital diagram from the beginning of this problem and instead look at it on its side. Look at it like this. So right here is the Earth, and now here's the Earth's equator, we'll say like so. And then let's say that you're standing on the equator, like so. And then we have, at some altitude above the ground, a satellite. And the satellite is orbiting the Earth such that, for example, if you were standing here on the equator, you would see the satellite straight up 24 hours per day, 365 days per year. So how can a satellite be in orbit about the Earth if you always see it at the same point in the sky? It's because as the Earth rotates, the satellite is rotating around the Earth with you. Basically, the following happens. My left hand here is you at the equator. My right hand is the satellite. And as the Earth rotates, the satellite orbits the Earth like so. So relative to you on the surface of the Earth at the equator, for example, you always see the satellite straight up. This will only occur, however, at a very specific altitude above the equator, and it will only occur above the equator itself. For example, I could, if I wanted to, have a satellite over here on an angle at the same altitude above the Earth as this point here, but as this satellite orbits the Earth like so, and the Earth rotates, will it always be in the same position in the sky relative to the surface of the Earth? No. So a geosynchronous orbit technically is only above the equator for this reason. What we need to do in this particular problem is find this distance right here that the satellite is above the ground. Let's refer to that as h. Now the r on my diagram from earlier is the distance from the center of the Earth to the satellite. What we need to do in this problem is use Kepler's third law, but not solve for t, but instead solve for r. Once I know what r is, I'll then subtract from it the radius of the Earth to get the altitude above the ground. Now, I said a moment ago that the period of the satellite's orbit is known. What is it equal to? It's not written down specifically in the problem, but what does it have to be such that it always maintains the same position in the sky as seen by this guy here at the equator, for example?
24 hours.
It has to be 24 hours, that's right. So the period is 24 hours. Anybody remember how many seconds there are in a day? 86,400. Very good. So that's the orbital period of the satellite. Okay, now this is once again just Kepler's third law. So here's then how I wrote Kepler's third law for this problem a few minutes ago. I just erased it. So let me just recopy it myself. So now what we're doing here in this example is we're solving for small r. Once I know what small r is, then I'll just subtract out from it the radius of the Earth. That will give us the altitude above the ground. As we'll see, this is a really big distance. So now I'm going to cross multiply this stuff from the parentheses over to the other side, and then take the cubed root of both sides. When I do, I end up with the following expression here for small r. It's this right here. And then I'll take the numbers, g, the mass of the Earth, and the period, 86,400 seconds, plug all that junk in, take the cubed root, and I'll get a distance here in meters. As we'll see, it's actually pretty big. So, calculating it out, first of all, I have g, punching that in appropriately, times the mass of the Earth, throw that in as well, times 86,400 squared, and then divided by 4 times pi squared, and then take the cubed root of all of that. You just raise it to the 1/3 power. And it's a pretty big distance. It's about 4.2 times 10 to the 7th meters. That's 42,000 kilometers. Now, 42,000 kilometers is small r. To get the altitude above the ground, the distance h as it's called here, what I have to do is take small r and subtract from it the radius of the Earth, which is about 6,400 kilometers. So subtract out appropriately, minus that, and you end up with about 3.6 times 10 to the 7th meters. That's about 36,000 kilometers. And that's way out there. It's about 1/10 of the distance from the Earth to the Moon. So this is far above and beyond low Earth orbit. But in geosynchronous orbit, that is, for example, where we have a large number of both communications and weather satellites. For example, with communications satellites. The communications satellite that controls both DirecTV and Dish Network, it's the same satellite. The two companies are using it, are positioned above the equator at an altitude of 36,000 kilometers above the ground itself. Now, those of you that do have a satellite dish, in which direction in the sky is it pointing? No. Although that's a good answer. Sorry? Yeah, it's actually pointed towards the southeast. The reason for that is because the satellite, the communications satellite that is used by both of those companies, is 36,000 kilometers above the equator south of Texas. Texas is basically the middle of the country, so your satellite dish is then therefore here in the western portion of the country, pointed towards the southeast for this reason. And the satellite, relative to the surface of the Earth, is always at the same point in the sky. So you never have to go outside and reposition your satellite dish or anything like that for this reason. Now, when you watch the weather on the news, when they show you the time lapse of the weather patterns over the course of hours, for example, does the perspective of the camera ever change? No, it's always the same view. So in other words, the weather satellites are also in geosynchronous orbit. They maintain the same position relative to the surface of the Earth. So going in an enormous ring all the way around the Earth up in geosynchronous orbit, there's about a dozen weather satellites. That's actually enough to cover the entire Earth. When you watch the weather on the news, it's just coming from one of those satellites. So when you watch the weather, for example, they'll show you close-ups, for example, of what's happening over LA. And they'll pull the camera back, they'll show you what's happening in the western United States. They can even pull the camera back even further and show you what's going on in the entire northern hemisphere. The reason for that is because the camera is attached to the satellite that is way out there. It's in geosynchronous orbit, 36,000 kilometers above the surface of the equator itself. Yeah.
Are these satellites government owned or are they?
Huh?
Are the satellites government?
So what companies do, for example, is that in some cases they'll build their own. They will then contract out to the government and now also with private companies, like for example SpaceX, they actually launch it up there. Or they will rent out essentially a communication satellite that is used by the United States government for other reasons. So when it comes to communication satellites for satellite TV, for example, and also the weather satellites, they're all up there in geosynchronous orbit. Now, at the beginning of class next time, I'm going to begin with kind of a follow-up to this example of a nice possible application of geosynchronous orbit. We'll see that at the beginning of class next time. Okay, now, during lunch today, I decided to make a slight change to the WebAssign. I announced this on Schoology during lunch as well. But what I've decided to do for the honors physics classes is do the remainder of the WebAssign up until the next exam, which is basically late next week. I'm just having it done all at once. In other words, it's not due on this Friday. I'm just going to do the whole thing on the 21st. Now, that includes these guys here, plus some additional problems that I'll put on the board next time in class. But I'm basically just going to do one big WebAssign assignment, due at the end of next week. This is also the same for the other honors classes as well.
Is our test Tuesday or Thursday?
It's Thursday. It's Thursday. Exactly.
Could we in theory now do 7, 14, 21,
Well,
23?
first of all this stuff right here in chapter 5, that's like bank curve problems and stuff like that. This stuff you can do right now. And yeah, you could do this stuff as well. So don't dawdle on it. Definitely get a start on it, but I am giving you guys a breather.
Because I looked at it last night and I couldn't do
Yeah, but
this.
now you can do the early stuff at 6. You can definitely do the early stuff at 6. Okay? All right, that's it.
Our test